is Paavola and you're watching the video abstract for decoherence control in different environments paper which can be found in the arXiv. This work has been done in collaboration with my supervisor Maniscalco here at the Turku Center for Quantum Physics, University of Turku. And in our paper we consider two schemes to control decoherence. We use as our system a simple quantum harmonic oscillator that is linearly coupled to a bosonic heat path. There exists an exact master equation, the Hubbard-Zhang master equation, that describes the dynamics in this case, and that allows us to obtain the correct short-time non-Markovian dynamics. We work in the high-temperature weak coupling approximation case, and the first scheme to control decoherence is based on engineering different reservoirs. This can be done experimentally, for example in the trapped ion case. And we consider the ohmic, subohmic and superohmic spectra, plus a resonance parameter which defines how resonant our system oscillator is with respect to the peak of the reservoir. It's defined as the proportionality of the system cutoff to the system oscillator frequency to the cutoff frequency of the reservoir. The quantum harmonic oscillator contains both highly non-classical and classical-like states, and we consider initially a highly quantum state, the Schrödinger cat state, and we want to see how these different environments cause the decoherence into a statistical mixture. And we eventually find out that the ohmic spectral distribution induces the least amount of decoherence. We measure the decoherence by the fringe visibility function, which essentially gives us how the interference term in the Wigner function representation of the Schrödinger cat state is decaying. The second decoherence control scheme is based on quantum Zeno effects, and here we consider an initial Fock state. And by performing frequent non-selective measurements, checking if the state is still in its initial state, we find that whether one has quantum Zeno effect, which is the inhibition of the decay of the state, or the anti-Zeno or inverse Zeno effect, which is the acceleration of the decay, that depends both on the reservoir parameters and the measurement time interval between the measurements. And we find out that the occurrence of the Zeno or anti-Zeno effect is very sensitive to these parameters. For example, in the superohmic spectra, you can have, by slightly varying the resonance parameter, you could go from having Zeno-type dynamics to anti-Zeno effect, completely changing the time evolution. Moreover, in the subohmic case, there exists always a crossover between the quantum Zeno effect and anti-Zeno effect, so by changing the measurement time intervals you can control whether you have the Zeno or the anti-Zeno effect. Because of the very rich dynamics of quantum Zeno and anti-Zeno effect, this type of system is very interesting in studying the fundamentals of quantum physics, like the quantum to classical transition, and we hope that some experiments might come along to examine this region. I thank you for your attention.